I think there's handing out some 3D glasses because I've come to tell you today about the work we're doing studying insect 3D vision. So I thought I'd start off with what is 3D. I guess probably everyone's been to see a 3D film. This is a still from Avatar. And hopefully if you put on the glasses, make sure the red lens is over your left eye, then you can see this percept of depth which the 3D vision gives you. So red over the left eye is going to work better. No worries. So we're all kind of familiar with 3D vision. It's defined as the sensation of depth that you get because you have a slightly different view of the world through your left and right eyes. So how does it work? Well, in everyday life, you look out at the world through your two eyes, and it's kind of amazing, that fact, isn't it? It's not something we think of a lot about, that you are actually viewing the world through these two windows, but your brain fuses them into one unified view of the world. But they actually get slightly different points of view. So, for example, if you're looking at a distant mountain, and you're looking at the mountain, so by definition it's falling at the same point in your left and your right eye, but let's say there's a tree in front of that mountain. Well, you'll notice that the tree is actually to the right of the mountain in the left eye's view, but it's to the left of the mountain in the right eye's view. So you've got this disparity between the two eyes' images. And kind of amazingly, your brain is able to pick that up and use that information to tell you about the distance of different objects. So here's an example I took. It looks like I've got the same photo just replicated, but actually they were taken from slightly different viewpoints, and they've therefore got slightly different images, as you can see if I display them in alternation. So now you can see the differences, and if I put those images up in red and blue so that you can view them, present them separately to each eye, then hopefully you get the 3D impression. Is that working for most people? Great. Okay, so that's 3D vision, that's great, but why should we study that? Why should people like me spend time trying to understand how it works? Well, I'm going to give you three broad reasons, and the first one, and the one that motivates me personally most, is simply the kind of basic scientific curiosity question. And I think it's really going to help us understand how the brain works, actually. So it's kind of amazing, isn't it? We see the world, but how does that happen? We've got electrical activity and nerve cells in our brains. We know that's involved somehow, but how? How can firing of action potentials in nerve cells somehow create conscious experience? Well, that's a huge question, but stereo vision is actually a kind of good model system for studying that. It's sort of simple enough that we feel like we can make a start, but sufficiently complex that the answers are going to teach us things. And Steven Pinker, in his book How the Mind Works, which I'd really recommend, has a great section on stereo vision where he goes through some of the reasons why stereo or 3D vision is a good model system. It's also got various implications for the clinic. So actually manipulating your two eyes and pointing them in the right direction in space is a challenging problem for a brain, for a nervous system, and it goes wrong quite a lot. So actually in developed countries, binocular vision disorders such as a squint or strabismus where one eye turns out or in are a major cause of visual impairment, especially in children. So we hope that understanding more about how our eyes normally work together, including 3D vision, could help us understand how these problems arise and, of course, perhaps suggest new treatments. And just a quick plug, in one of the other projects in my lab, we're actually using new 3D tablet computers to develop a 3D vision test for use in NHS eye clinics. And the idea is that it's going to be more fun for small children, but also more accurate. And I've got a couple of tablets upstairs. So if you want to try that out during the lunch break, then please do. And there's our website if you want to find out more. And thirdly, of course, there are all sorts of applications of 3D vision and 3D displays. So we've already mentioned entertainment, the 3D films and so on, but actually in medicine as well. So increasingly nowadays in surgery, robots are being involved, and the surgeon isn't operating directly on your body, but he or she is controlling a robot and doing that, viewing an image of your body on a 3D display. So of course then there are questions about, well, how accurate is depth perception in those displays? Are there things we could do to improve the image? And understanding stereo vision, of course, is going to be highly relevant to that. So some of the work I do is in collaboration with 3D television and cinema companies. So it's got lots of applications. So hopefully that's convinced you that 3D vision is important. So my next question, who has it? 100 years ago, the answer was very clear. It was obviously a very complicated ability which only the higher animals, such as man, could possibly have. But we now know that's actually completely wrong. And we've discovered 3D vision in all sorts of organisms. So yes, in humans and in our primate relatives, and of course in the machines that we make, but also in other mammalian predators like cats, in bird predators, so owls and falcons, and amphibian predators like toads, and I guess surprisingly also in prey animals, so horses and sheep. When I was a kid, I read, oh, you know, they have eyes on the side of their head, they don't have 3D vision. But no, we actually know that, yes, they do have 3D vision. And perhaps most surprisingly, and of interest to me, even some insects have 3D vision. So this is a praying mantis, and we discovered fairly recently that at least that one insect does have 3D vision. So right about now, people tend to ask me, how can you possibly say whether or not an insect has 3D vision? So I want to talk a little bit about how we discovered that, and it was actually the work of Professor Samuel Russell in a series of papers beginning in 1983. He used the behaviour of mantises. So praying mantises are ambush predators. They just lie in wait, very still, camouflage, trying hard to look like a leaf or something. And then when their prey comes within their catch range, they strike out with their spiky forelegs and grab it really quickly. So Russell had this idea that, well, maybe they're using 3D vision to do that. So they're kind of triangulating back, using the fact that they have two eyes set far apart on their head. And they know that prey is in range by measuring this angle that I've labelled delta there. How could he test this? Well, he had this fabulous idea of just putting prisms in front of the animal's eyes. Prisms, as you know, bend light rays, so you can see hopefully the little bend happening as the light passes through the prism. But of course, the insect isn't going to take that into account, so it's going to perceive light as coming as if the light rays were not bent. And what that means is that when the prey is really over there, the mantis is going to perceive it as being much closer and within range, critically. So it'll reach out and try and catch the prey, but it'll be in the wrong place. So from the pattern of errors, you can deduce, and Russell did deduce, that praying mantises have 3D vision. So I think that's a really beautiful series of experiments. And when I discovered that, I was really excited to think, gosh, insects have 3D, that's amazing. And actually it brings to 4 the total number of times that we know 3D vision evolved. We believe it evolved in the common ancestor of all mammals, but we think it evolved separately actually in birds and amphibians and of course in insects, because their eyes are completely different. So that means evolution has discovered 3D vision at least 4 times, possibly more. And as someone who works on 3D vision and tries to figure out how it works, I was like, well, gosh, I wonder if it works the same way in all of them. Does insect vision do the same kind of things as human 3D that I'm familiar with? Or does it work in some completely different way? And no one had really gone and attempted to answer those questions since Russell. So I wrote a grant application to the Leverhulme Trust and convinced them that this was a burning question we needed to know about. And we've started the Man, Mantis and Machine project aiming to compare stereo vision in human beings, in praying mantises, and also in machine vision algorithms. And I want to give the credit to these my 3 postdocs who are working on this project. So they're the ones who actually do the work. Now the first problem we had was, okay, how are we going to display 3D images to an insect? People sometimes ask, why do you need to display images in 3D? Is it not seeing in 3D all the time? Yes, it is, but we need to be able to manipulate that, to make mistakes, if you like, just like Russell did. If you just have the animal reach out and catch a fly naturally, you don't know what it's responding to. How did it know where that fly was? Maybe it sensed the air currents, or maybe it was the change in size as the fly approached. And you can see that Russell's prisms enabled him to tell it could only be responding to the 3D. But the prisms are fairly limited. You can shift objects closer and further away. But we wanted to display more elaborate images to the mantises, so we needed a better 3D display. And that took a long time and a lot of work for Vivek. And eventually Vivek came up with a really good solution, which looks like this. 3D glasses for insects. Now we've got a few shots of our mantises wearing their 3D glasses, which Vivek puts on very neatly with a little dab of beeswax there. We chose beeswax because, of course, it's non-toxic. It melts very quickly with a bit of heat, and then he puts the glasses on, it solidifies, and then there's the mantis wearing its glasses. So they're basically the same idea as the 3D glasses that you have, except that insects, well, most insects and certainly mantises can't see red light at all well. So we used blue and green filters instead of red and blue or red and green, as people often use for humans. Actually, they work even better for mantises than they do for humans because mantises are colourblind. So when you view through those old style 3D glasses, it looks a mess really because you're aware that one eye's seeing blue, one eye's seeing red, and that's of course why they're not used in cinemas anymore. We've got better technology. But for mantises, they should be just fine. So just to go through a little bit about how this works, this is the sort of image that we would put up on a computer screen in our experiments. So we'd have a target, a little simulated fly, if you like, for the mantis, and we'd draw it in blue for one eye and green for the other eye. So the idea is that because the insect is viewing it through these filters, if you see what I mean, this filter here only lets through the blue light, it blocks the green light. So the green dot appears as a black sort of hole where there is no blue light. And so you get these two different images. And because the animal's colourblind, it wouldn't perceive the colour difference, it just sees something like that. So in other words, we've got a difference between the position of the object in the two eyes. So we've been able to introduce a disparity, and then we can test, okay, is this working? Are our 3D glasses really giving this insect an illusion of depth? So to try and answer that, we manipulated the geometry, if you like, what we put on the screen. So here are the two images I just showed you, but in the top and the bottom I've just swapped over which disc is green and which is blue. And that doesn't sound like a big difference, but you can see that for the one on the top, that's now simulating an object in front of the mantis within its catch range, whereas at the bottom, it isn't. It's an object a very, very long way away, if you like. So then this is the kind of crucial experiment. So we put the object on the screen and we have it move around in what the mantids evidently find quite a tantalising way. They like that sort of swirling pattern. And this mantis, I don't know if you can see its little head, it's sort of moving occasionally. It can definitely see this thing on the screen, but it's not doing anything because the screen's 10 centimetres away, that's well outside their catch range, and the geometry is such as to indicate that this simulated bug, it doesn't really make sense. It's a very long way away. So the animal's just watching. But if we put up the same image but swap over the blue and green, now that simulates a virtual object in front of the animal within its catch range, and so it reaches out and strikes and tries to get it. It's kind of amusing. You see kids doing this sometimes with 3D films. They're like, wow, that's amazing, and they try and grab, Nemo or whatever it is. So if you sort of measure the actual quantitative data, we find that the mantis strikes over half the time for the crossed disparity condition and never strikes for the other one. So that's a really clear demonstration that our 3D glasses are working correctly. So that's all great, and now we can move on to ask the questions that really sort of interest me about 3D vision. And one of them that we're trying to understand is, can insect 3D break camouflage like human 3D can? What do I mean by that? Well, that's something that people have used 3D for basically since it was discovered. So the guy that I quoted earlier, Major Ives, was actually writing in a book on aerial reconnaissance published after the First World War. And he has a section on stereo photography. And as he explains there, he says that bridges and observation towers, no matter how carefully painted and skillfully camouflaged, jump into view when you look at them in a stereoscope. So you're using the stereo photography to reveal structures and break the camouflage that people have tried to conceal them with. So here's an example, a sort of pattern of random squares scattered across a surface. And if I were to say to you, can you find a circle or a disc in that pattern? I don't think you could. But you may have seen one very briefly there. So if you shift the dots, then a circle starts to become defined. And again, if I display that in 3D, then you can see a disc standing out in depth. And this image, you can feel free to change the glasses round if you like. So you should see it change from a disc standing out in depth one way versus a circular hole in the surface when you swap the glasses over. Is that working for people? So you can think of this, imagine it like there's a disc that's perfectly camouflaged. It's got exactly the same pattern as the background. So with one eye, you can't see it at all, but with two eyes, your stereo vision reveals it. And this camouflage breaking aspect of stereo is believed to be really important for humans and other primates, and we think it might be a really important reason it evolved. Now, you'd think that might also be important for insects, but it turns out our preliminary experiments are suggesting that insect 3D doesn't work like that and can't break the camouflage. So the mantises can only see things when they're moving. And when they're moving, they've kind of broken their own camouflage, haven't they? They've given themselves away. And the insects can use their 3D vision to see how far away a moving object is, but not to find it in the first place. So that's a key difference between human and insect 3D, and kind of suggests that insect 3D isn't as good, which is kind of reassuring for us, right? We've got these enormous brains, so it would be a bit embarrassing if a mantis with a sort of 1 millimetre sized brain could do as well. But actually, we were able to come up with some images where the insects, in fact, do outperform us. So in particular tasks where I guess they're designed to be better for insects, we actually find that the mantises can do better than the students we have come into the lab to do the experiments. So maybe humans shouldn't be too smug after all. And I guess in particular, with the thing about evolution, it's not like one thing's better or worse. They're kind of optimized for different niches. So I think studying insect vision, as well as being fascinating in its own right, I hope you agree, I think it could potentially have some spin-offs. So we have computer algorithms to do 3D vision, but they're mainly based on human 3D vision. And so they're kind of complicated and elaborate and can do all these amazing things like break camouflage. And that might be what you need for some applications. But, for example, increasingly, really lightweight autonomous drones are becoming important. So there's a British soldier with one that apparently they use in Afghanistan, and there's a prototype drone that was designed to find avalanche victims. So increasingly, these are going to be part of our life, I think. And in such an application, you might want a really kind of quick and dirty 3D that doesn't work so well, but it does the job, and it's really low cost to implement and can run on a very low power system. And of course, that's exactly what insects give us. So that's sort of summed up some of the work that we're doing on insect 3D, and I'll be delighted to answer questions if you find me over lunch. Thank you.